My name is Izzat Suffian, currently working as assistant professor at Faculty of Pharmacy in International Islamic University, Malaysia. So for today, I would like to share with everyone a bit of my expertise in drug delivery and also in nanomedicine, especially when we're going to talk about tackling the COVID-19, or we call it the virus as SARS-CoV-2. So I think I will share my slide with everyone here. Okay. Okay, can you see the slide?
Yeah, okay.
Okay, good. So I think we shall start now. So the title that I'm going to share with everyone today is Nanomedicine, the new magical item to fight COVID-19. So if you look into this slide, basically these are we call it as electron micrograph of TEM, or the transmission electron microscopic images of the virus, or what we call it the virus as SARS, SARS-CoV-2, is SARS-CoV coronavirus type 2. So on the left is the black and white, and then the right also the colored one. So you can see the structure of the virus itself is like it's about spherical, nearly spherical, and then you get some kind of spike around the outer part of the virus, that's how we got the name of corona, which actually the corona also means as crown. So because of the spike of the virus, that's why we call it as it looks like it got its own crown, and that's why we name it as the coronavirus. So exactly like before we go further with the topic, we go back with what we call as the coronavirus or the COVID-19. What exactly happened, how does it happen, and so on. So basically SARS-CoV-2 is actually not the new virus, not the new coronavirus, actually the 7th coronavirus that happened to infect humans. So previously we have SARS-CoV-1, which has happened in 2002, SARS-CoV, which has happened in the mid, and now we have SARS-CoV-2. So this SARS-CoV-2, or the disease, we call it the COVID-19, it's actually firstly discovered in Wuhan, which is in China. So it's actually the capital city of Hubei province in December 2019. So it happened about like 6 months ago. And then it has been identified by the scientists and researchers in China as a new or novel envelope RNA virus, or RNA beta coronavirus, which actually, if you look just in general, it's similar as SARS-CoV virus, but then because of the RNA is a bit different, so it's actually a new the envelope RNA virus that we call it SARS-CoV-2, because the envelope of the virus is mimicking SARS-CoV, but the RNA and so on a bit different, and also the spike also a bit different. That's why we call it SARS-CoV type 2. So what happened when you got infected by this COVID-19 or the SARS-CoV-2 virus? So usually we got a headache, someone got fatigue, dry cough, runny nose, and fever, and even sore throat. So this is quite common. So sometimes people got mistaken as a normal influenza, but also but because of this quite similar symptoms, when people develop this kind of symptoms, it is advisable for them to go for checking and diagnose, for example, do the swabbing and to test whether they are positive or negative with the virus. And if you look further, in terms of transmission, when you say it's not like airborne, basically like anything of the what we call it as the droplet comes from when you're sneezing, when you're coughing, and also when you're talking. It happens like in the air, and then you got contact with other human, then you got transmitted with the virus. Also animal contact, so we know the source of the virus actually from the bat. So actually if you think, so what happened in China, people consume bat as part of their staple as their food. That's why they got infected by the virus. Also human contact and other contaminated objects that got contaminated with the virus can cause you to be infected by this COVID-19. So if you look at the situation globally, so in the world with the COVID-19, you can see now at the moment at 26 May 2020, the positive cases happen throughout the world. We got is like more than 5.6 million cases throughout the world, which actually the leading in the United States. Even though the firstly happened in China, China managed to control it and managed to deliver and give some, and we can see they have managed to control them very well, but somehow in the United States, you can see it's increasing a lot. And then total death happened throughout the world is more than 352,000 deaths throughout the world. So in Malaysia, we have a very few number of deaths. So we only have 115 deaths recorded so far until today, and even the positive cases just about nearly 7,000. So we managed to control. But if you look into the graph on the right side, you can see the increasing number of the positive cases happened after middle of March. So in Malaysia, we started to, we're not totally locked down, we call it as movement control order. So it's not 100% locked down, but it's advisable for all the citizens to stay in the house, and also certain industry have been closed down. We started at 18 March. So actually throughout the world, the cases increasing at the middle of March and until today. And even the death also is increasing a lot. So this actually happened with the coronavirus. So the issue here, why this coronavirus or why this COVID-19 has been really global pandemic throughout the world, because it's totally new. The behavior, even though it's similar with the SARS-CoV, but then it's really aggressive in terms of infections. It's really aggressive in terms of the symptoms. And then the way it transmitted to humans very fast compared than the SARS-CoV, which happened in 2002. And then even until today, we don't have any vaccine or any specific drugs that can use to cure the corona or the COVID-19. So we talk about the cure because of, as I said earlier, there is no particular or specific treatment that actually helping to cure COVID-19 or the SARS-CoV-2. And then, so what happened with the current hospital, clinical, what they use the anti-HIV drugs, they use anti-malarial drugs to control the symptoms and also to control the replication of the virus. So it's not totally, we cannot say that the drugs that we use is purposely used for the COVID-19, but we manage to use this combination of anti-HIV drugs and also the anti-malarial drugs to manage control the replication of the virus up to the level is undetectable. So we not totally say the virus, so for those, the patient has been positively infected, but the virus is totally eradicated from the virus. It just based on the treatment being done by this combination of the drugs, the numbers of the virus is undetectable based on what we are using the PCR, the RT-PCR. But we cannot say 100% that particular person is totally no virus being infected. It's just that based on detection, we cannot detect anymore. So that's how we say it's considered as negative with the COVID-19. But then you can see from the news that certain individual that actually been infected back of this COVID-19 or the SARS-CoV-2 virus, even though they'll be infected at the first time. So there are a lot of things need to be studied and need to be researched by a lot of scientists, also the doctors, because we still couldn't understand the 100% behavior of this virus, whether if you say it's undetectable, whether this virus actually hidden or actually is being complemented with the our other cells, and then that's how it's become dormant in the body, but somehow it's activated after a few weeks or a certain time. So there are a lot of things that we need to understand about the behavior and also the properties of the virus. But somehow a lot of scientists and researchers manage to do some kind of like screening of the structure of the virus. As you can see on the right side of the virus, these are the 3D structure that have been released by CDC United States about the structure of the virus. You can see that from 3D image here, they got 3 different type of proteins available on the surface of the COVID-19 or the SARS-CoV-2 virus. What we call it as the S protein, M protein, and E protein. So S protein is referred to as the spike protein, E protein is referred to the envelope, and the M protein is referred to the membrane. So basically, the one that actually helped to for this virus to actually conjugate to our body cells or our tissues or in the lung is actually the S protein. See, these are the spike, the red one, actually that actually bound to what we call as the human ACE2 receptors. So this how exactly how when you got infected by the COVID-19 virus, then it goes into your body, and then this S protein will bound to this what we call it as human ACE2 receptors, and then afterwards you will start to release its RNA inside the cells and cause all this study. I will come back with this one. So this is what we understand so far about the SARS-CoV-2 virus or the COVID-19 virus. So let's jump a bit about what we call as nanocarriers, because the topic is about nanomedicine. So what we call it as nanocarriers? What are they? So for those who don't understand what are the nanocarriers, so or nanoparticles and so on. So we go with the term first. So the nano means the size. So refer the nano size is at 10⁻⁹. So it's very, very small if you compare than the micro. So it's 3 times of the 10 smaller than the micro. So it means it's really, really tiny, it's really, really small. So when we call it nanocarrier, it means that there's certain carriers that we developed that's really in nano size. So when we call it a nanocarriers, it's actually very small, we call it in nanometers, and there are got several types of nanocarriers available. So these are some of it that I managed to share with everyone here. So we call it a biodegradable polymeric nanoparticles, meaning that the nanoparticle is made by a polymer base and also biodegradable, meaning that if internalized into your body, it will degrade and safe to be consumed or to be used inside the human body. And we have dendrimer here, and also we've got solid lipid nanoparticle. It's a lipid base but solid in terms of the outer, and then we have also the internal. And we have liposome, also based on lipid, so it is a bilayer of the lipid. And we have magnetic nanoparticle, so meaning that the nanoparticle have a magnetic properties. For example, you have iron oxide that we can use to deliver drugs or something. And we have based on carbon. So we have carbon nanotube, and now we have graphene. We have the diamond nanoparticle, so anything based on carbon. But this one is a carbon sheet that we make into a tube kind of structure. And also we have virus-like particle, so meaning that it derives mimic. Okay, sorry, I just disconnected. Can you hear me again?
Yes, yes, can hear you.
Okay, sorry, I'll continue back. Okay, sorry, got some problem of internet. Okay, we continue. So I just share with you about the type of nanocarriers. Now, what are the advantages, especially when we talk about in biodiagnostic and therapeutic, because we are facing COVID-19, which are the virus. So as I said earlier, they are small dimensions. And then when it comes to size, usually when we define as nanocarriers, we define as from 1 nanometer to 100 nanometers in terms of size. Some of might goes up to 300 nanometers. So it's really, really small. And then because of the smaller size, when we talk about in terms of like in 1 ml, it's a 1 milliliter of volume of the nanoparticle, because very small, meaning it provides you a very large surface area. Because of it provides you a very large surface area, it allows you to do a lot of modification. It allows you to deliver drugs or any biomolecules or anything that you want to deliver to your target, in our case, the virus, in very small amount, but it managed to give a high efficacy because of the large surface area. And as I shared earlier in the previous slide with the previous slide, you can see that they got a various molecular structure. You can make from many types, from inorganic compound to organic compound, and up to the protein base or the virus base. So with this kind of flexibility of using of material to provide of nanocarriers, so you can adjust based on what are the things that you want to deliver, what you want to target with. So for example, you want to target virus, so you need a material that can penetrate, that can bound to the virus, that can cause the virus to die or to be detected. And if you look into this one of the large surface area, the fourth advantage of these nanocarriers, like it can deliver biomolecules, for example, drugs or antiviral drugs here, and anything of imaging probes carrier. So meaning that you can use this nanocarrier to somehow it become a sensor to detect where are the virus. Once it's bound or conjugated with the virus, it can detect the location of the virus or how much the virus already infected certain individual. Okay, let's come back. So I share with you the virus about the COVID-19, and then I'll share you about general information about the nanocarriers. So if you look further into the COVID-19 virus or the SARS-CoV-2, if you look into here, actually, scientists or researchers have found that the size of this virus, one virus, is about 125 nanometer in diameter. So if you look into a logic situation, if you want to target the virus or you want to detect the virus, logically you cannot use something that bigger than the virus. So meaning that if you have something like, for example, 1 micron in size of sensor to detect the virus, it's quite impossible because you cannot detect a per individual virus easily because your sensor is bigger than the virus. So a lot of scientists already discussed this one. I got a few papers, even in Nature just published one as well, that for you to target or to localize the virus itself, you need something that's smaller than the virus. So meaning that you need to develop some kind of a system that are smaller than the 125 nanometer in diameter. So in this case, as I shared with you earlier, nanoparticles or nanocarriers be known in nano size, so from 1 nanometer up to 100 or more, because we want to detect something that's smaller, in this case 125 nanometer. So scientists have proposed to use nanocarriers that in terms of size 10 to 30 nanometers as the best size to actually detect or bound to the virus. So here, for example, we have dendrimer, we have liposomes, also we have the protein nanocage. So these are the size that have been proposed as what we call as the best at the current situation. So why 10 to 30? Why not more than 30? Why not less than 10? So remember that our purpose, not just to detect the virus, we want, is possible, to actually cure or kill the virus, meaning that we want to deliver something else. So meaning that if you have something smaller than 10, it's quite impossible for you to encapsulate drug inside this nanocarriers. And if you have something bigger, it might cause hard for the nanocarrier to bound to the virus. So the ideal size being proposed is 10 to 30 because certain drugs is quite still can be encapsulated inside this size of nanocarrier. So if it goes smaller, it's a bit hard because certain drugs also much bigger, so it's impossible for drugs to actually conjugate it to the nanocarriers. Okay, so now I say on that part, so because of the advantages of the nanocarriers can be modified, it's up to you. So it's kind of ideal kind of like system that you can modify based on your target or on your goal. So if you want to modify them for detection or diagnosis, you can modify the surface. If you want to deliver certain drugs, you can encapsulate anything, and based on, as I said earlier, based on what your target, you can use different materials or based on different purpose. Okay, because of COVID-19, you need to understand COVID-19 mainly is infected the lung of the individual. So it goes into the lung, so mainly that's into the respiratory system. So the best route in terms of delivering drugs or delivering any curing system or therapeutic system, the best being studied right now is the intranasal will be the best because of the intranasal. If you spread intranasal drugs through our respiratory system, it will immediately distribute it into our lung quickly rather than intravenous. But it depends of the stage of the infection, because as you know, certain cases discovered that the virus have been goes everywhere into the body, not just into the lung. Sometimes it can found into the liver and other parts of the organs. So if that the case, intravenous route also being is great for you to deliver the drugs. As I said, because of the flexibility of the nanocarriers can be modified, so you can conjugate your nanocarriers to therapeutic agents. So in this case, you can conjugate with the antiviral drug that being used at the moment. For example, the combination of anti-HIV drugs or the anti-malaria drugs can be conjugated to the nanocarriers and modify the surface. So these are, despite, as I said, it's bound to the human ACE2 receptors. So scientists propose that for the nanocarriers to be modified on the surface, and then you got some kind of the binding moiety that will bound to the S protein of the virus, meaning that when you deliver the nanocarriers with the drug inside, so with the therapeutic agents inside, we will not just randomly deliver the drugs. So we will specifically deliver the drugs to only be delivered to the COVID-19 virus. So you will avoid any or reduce as much as possible of any side effects from the drugs. Because, for example, if you deliver the anti-malaria drug, if you're giving as intravenous, for example, so then the drug will still be exposed to our healthy tissues. So what happens? It might cause a problem with our tissues in terms of side effect, especially if you've been administered with the drugs for a longer time. So with this modification of development of you encapsulate or conjugate antitherapeutic agents inside or the surface of the nanocarriers, you will specifically deliver your nanocarriers with the antiviral drugs to only to the COVID-19 virus. So you will have a much higher efficacy of the drug delivery to the virus, and then instead of using it with the current dose, perhaps you can reduce the dosage of the drugs, because the drugs only deliver to the virus and it still works as the same with the current proposed dosage in the clinical system. And also, you can conjugate your nanocarriers with diagnostic agent. So with the same system, you bound the nanocarriers with the spike. You can use this kind of like a system to actually localize where are the viruses. So, or how much of the viruses been infected to the certain individual. So based on that one, you will allow for doctors somehow understanding, okay, now the virus is not just localized in the lung, perhaps it already goes to other parts of the organs. And also you can see at how much intensity of the virus being localized. If you can see like, okay, more of the virus infected of the right part of the lung, so doctor can adjust in terms of like therapeutical or deliver the drugs, instead of you deliver only to the whole lung, perhaps it can just specific to give higher dosage into the right lung where it have more infection. So with this kind of diagnostic agents, it helps for the medical doctors and for those in the frontliners to understand in terms of the treatment, rather than you hope for the drugs to be distributed to the whole body, and then hopefully you will reach where are the virus being localized. And with other modification, because we want to do the best intranasal or intravenous route, with the drugs, you can modify that to cut emulsion or in a solution form. And then if it's emulsion solution form, you can put it in the nasal spray, just spray inside, or then you can use the same thing to be injected into the bloodstream. And then it will go everywhere. It goes distributed through the system and localized where are the drugs. So these are kind of like a very unique about the nanocarriers. And then when we say nanocarriers, when we say nanomedicine, actually the nanocarriers has been used for treatment, also for diagnostic. So because of this flexibility or universal of these nanocarriers, a lot of scientists have been focused, okay, while other people focusing into for the vaccine, why not the nanomedicine or the nanotech scientists focus into, okay, with the current treatment or what we can improve into for delivery or screening and so on. Because based on the WHO announcement, for the vaccine to be developed, it will take about 18 months minimum. And then it depends on the clinical trial, whether you're going to pass the phase 1 clinical trial, phase 2, and up to phase 3. We know that up until yesterday, in Australia or in New Zealand, if not mistaken, already announced they're going to start their phase 1 trial of the new vaccine. And then one also from the United States, also, not say or UK, if not mistaken, going to test their own version of the phase 1 of the anti-vaccine. So hopefully with the vaccine also, while they're doing with this one, we can somehow, in a different perspective point of view, to actually treat also or screening or diagnostic in terms of the virus infection. Okay, I'm going to focus on the diagnosis first. Okay, when I say diagnosis, like in the clinical, it is quite three common diagnosis system or imaging system being used in clinical. First, what we call is a fluorescence. Second, what we call it nuclear, and the third one we call it luminescence. Okay, I'll go one by one. So here is all the images I show you are the in vivo image of the imaging system. So with the fluorescence, what we can do based on the far rate, or we can use any other fluorescein to detect. So for example, you have a polymer-based nanocarriers. You conjugate with the fluorescence, for example, the far rate fluorescein with the virus. Also, you have a targeting moiety that specific target the S protein of the virus. Once your nanoparticle reach the virus, and then you do some fluorescence imaging, it will detect the signal from the nanoparticle. Okay, now you know your nanoparticle actually bound to the virus. So you can see high intensity, for example, in the lung. So you know that actually the accumulation numbers of the virus actually localized in the lung more compared to other part of the tissue. So this how helping in terms of the clinical doctors to understand, okay, where exactly the virus is now localized in the body. Because at the moment, what they do with this, with the testing, also the treatment in the hospital, they cannot really determine where exactly the virus localized. They already know based on the symptoms. If you see like the lungs become like full of the liquid, and then you know, okay, a lot of infection happened. But then if they need to scan each of the organs, it will hard. Give you the biopsy, for example, you need to do the, or you need to do the MRI, whether it's actually happened more, whether it's really infected to the brain, and so on. So a lot of things need to be done to actually localize or identify the actual infection or the actual location of the virus. So with the imaging system, for example, a fluorescence system, you can help to localize the location of the virus. But with the fluorescence, they got a limitation. Because the fluorescence signal got limitation, like it can be detected if the virus is in high number. So if we talk about a very tiny amount, just maybe the starting of the infection, it's really hard to be detected, the signal from the fluorescence, because the fluorescence got limitations. And also, if you can see, if for those who have experience working with animal with fluorescence, certain animal have a false signaling, and also with fluorescence, it can give you autofluorescent signal, for example, based on the food that being consumed by the animal. So with the animal, we can control the food, but we talk about the patient, we talk about the human. You cannot control like, okay, this particular patient A eating only food A, and this patient B only eating food A. No, you can't control. It's based on like the diet of certain individual. So it got limitation. You might have a false signaling happen with the fluorescence. So you can be used with fluorescence, but it got limitation, and in terms of sensitivity as well. So it is specific, but it still have autofluorescence happen from the food you consume. But in terms of sensitivity, it a bit less, because especially when, as I said earlier, if the numbers of the virus in the body system is still low. Okay, and then we talk about the nuclear. So the nucleus imaging system, they are using the radionuclide. So that means they're using the isotope or to detect the signal. So a same concept with the fluorescent, but instead of using fluorescein for detection, using radionuclide. For example, you use technetium 99M, or you use the 111 indium or from as the radionuclide to detect the signal. So what happened here? So you have a nanocarrier. So you conjugate with radio, or you not you conjugate. You label the correct term you use. You radio labeling your nanocarriers with radionuclide. For example, 111 indium. So you use that one, and then you inject, or you're giving the nanocarriers to the body system, and then when the nanocarriers bound to the S protein, then you can detect the signal comes from the radionuclide. A good about the radionuclide is really sensitive. So compare with the fluorescence imaging system, the radionuclide, the signal come from radionuclide is really sensitive, and that it can detect even at very low amount of the targeting location. In our case, is the virus. So if you use this kind of system, you can detect even a smaller amount of the virus even already infected in the body. It's still on it's still kind of like in the proposal stage, because no one yet been used a radionuclide to detect the virus. But then this also, the nuclear imaging system have been done with other diseases, including cancer. So people use the nuclear system, especially to detect if, for example, in cancer you have cancer, for example, cancer's early stage or non-tumorized cancer, you can detect wherever the cancer cells are. So a same concept it been proposed. You can use the same concept to detect the virus. So with the radionuclide, also is safe. No risk. There's no toxicity comes from the radionuclide. I know when it comes to, we talk about nuclear or radioactive, we have this kind of negative stigma. Oh my God, radioactive, put inside the body, I'm going to die. So we are using the gamma signaling. So we're not using the beta signaling. So using the gamma signaling to detect M is safe for the human being, because the dosage being used is already been determined is safe for detection. But with the nuclear system, we know the limitation with the nuclear system is in terms of the cost. It is expensive into the nuclear imaging system. And another thing with the nuclear imaging system is like you need a proper instrument for that. So for nuclear system, either you go PET imaging, PET, or you go with SPECT imaging, SPECT CT imaging. So not many countries, especially the third world country, have the access of this one. So they got a bit of limitation on this. Compared to fluorescence, it's much cheaper, but then in the detection limitation, they have it. But in terms of nuclear, in terms of the pros, very sensitive, very specific, but then of course it's a bit higher. Okay, that's with the nuclear imaging. And then the third one is the luminescence imaging. So luminescence is actually using, if you know, like the jellyfish and certain firefly, you know that it gives you light at night, right? So the light that come from the jellyfish or the light come from the firefly actually is luminescence, or it's some kind of a compound, a chemical compound that exists in nature. So with this one, it's really sensitive with the luminescence, but in terms of the detection is quite similar with the nuclear or fluorescence, but use the luminescence. But then it is much costly compared to nuclear because we have a limitation access of the luminescence. It's really much expensive. I think Anupam experienced while we were back in London before that when it comes to luminescence, you know how the haywire if you got mistake with luminescence studies, but you know it's really expensive. But it's really sensitive with luminescence, so you can detect the signal. And then, but for you to detect the signal, it needs a reaction from an enzyme we call it luciferase. So this enzyme will help for you to give signal. So compare then these three, between these three, fluorescence, nuclear, and luminescence. From my own, this is my own personal recommendation. I would prefer nuclear to be used in terms of like detection of the virus, because like in terms of sensitivity is high, in terms of cost it's not as, it's expensive, but it's less expensive than luminescence. And then it really much easier to be controlled in terms of like doing the formulation and so on compared to luminescence, because with luminescence we handling the enzyme, so you know enzyme is sensitive in terms of temperature or if you're handling and so on. So if the mismanagement in terms of the handling, you might not have some detection with the luminescence. But with nuclear, once you got the radio label, once you got the NANOCARRIERS with label radionuclide, it on go, just put in the be injected or put the nasal, then you can detect whatever it goes. Okay, that's in terms of the diagnosis. In terms of therapy, they got a few types of therapy being used, but I'm going to share what we call it in the gene therapy or siRNA delivery. So as been mentioned earlier, we know COVID-19 is RNA virus. So meaning that inside of the virus is got RNA or ribonucleic acid. So because we understand that it contains RNA, so one of the best approach is actually, why don't we knock down the RNA inside of the virus? So meaning that even though you being infected with the virus, if we knock down the RNA, it will not cause any symptoms, it will not cause any disease, it will not cause any complication to the patient. So because it's just an empty virus without the RNA, because the RNA that actually contain all the information, the RNA that actually that cause all these kind of symptoms, causing you to feel sick and so on. So if you manage to knock down the RNA, you'll be ideal. Like even though you have the virus, you knock down the RNA, then at least you settle like, okay, just need to clear the virus, but then the virus has no more RNA, so it will not cause any problem to the patient. So what is the sRNA? So sRNA is small interference ribonucleic acid. So it knows that small sRNA have the property to actually silencing or to knock down or any RNA. And then with the sRNA, you can customize them specific to which RNA you want to knock down. Okay, so in this case, we have already the mapping of RNA of the COVID-19. So we know specific of this RNA. So we need to synthesize the sRNA that's specific to knock down the COVID-19 RNA that we need to deliver them. So the process is simple for this one. So what happened when you have sRNA, you will silence the viral RNA or messenger RNA at particular stages in human cells, and also it able to inhibit any expressions of the homologous sequence in the target RNA because it's knocked down. And also it can provide complementary strands of apparent mRNA, and then later it will just silence or knock down the RNA. So these are the advantages of using sRNA delivery. But because of sRNA is ribonucleic acid, it's very sensitive in terms of like the blood serum and so on. So you can't deliver RNA or sRNA, just inject sRNA like that and to be delivered. No, if you exposed to the blood serum, it will degrade it immediately and will not function anymore. So using the nanocarriers, it will protect the RNA, and also we already have, for example, this we put the bounding targeting moiety. So here, imaging this one actually target the S protein or the spike protein of the virus. So it will bound to the S protein of the virus, then will internalize the virus and deliver this sRNA, and the sRNA will knock down the RNA of the COVID-19. So it gives you like, okay, instead of using drugs, using sRNA that's really less harmful instead of like the side effect from the drugs. And also RNA will not work with sRNA will not work with other RNA. It will only work to do the silencing or down with specific sRNA that you're being developed. So in our case, because we're going to develop sRNA that specific target the RNA of the COVID-19, and then it should be much safer, much specific in terms of to kill the virus. And this method have been tested not in COVID-19, but they already tested this kind of gene silencing or the testing of sRNA in hepatitis C virus. So they already test this system in other type of disease, in our liver disease, hepatitis C, and they managed to knock down or kill the virus. So you can go with this paper. So this paper by Kim, so from South Korea, from Korea University. So they use this kind of system. They managed to knock down hepatitis C virus. So if you use the same concept of this one, so here they use the nanocarrier, they use the liposomes, and then you have the cationic liposomes, so for them to actually complex with the sRNA. So if they manage to do this with hepatitis C virus, we can use a same concept, put some modifications to develop a nanocarrier that actually can target COVID-19 virus or SARS-CoV-2, and then also silence, knock down the RNA. So meaning that especially for those being heavily infected by the virus, or for this on top of we try to reduce the symptoms of what happened to the patient, we can also cure the COVID-19 virus. So we can use a same concept in this case, but handling the virus, you need a proper setup of the laboratory, and not many countries have the what we call it BSL-3 laboratory to handle the virus. So that's part we got a limitation in terms of doing the studies with the virus. Okay, I talked separately just now, one for the diagnostic, one for the therapy. So meaning that one used for diagnostic, one used for therapy. But this new paper being published by Itani et al. From Lebanon, Beirut, Lebanon. So they propose what we call is a theranostic approach. So what exactly is theranostic? So I talk about diagnostic, I talk about therapy, right? So theranostic is combination of therapy and diagnostic in one system. So instead of you use a separate system, so I mean one nanoparticle for diagnosis, one nanoparticle system for therapy, why don't we combine into one system that have multiple function? So it can use for therapy, it also can be used for diagnostic. So this paper, they propose to use a theranostic nanoparticle to treat COVID-19 patient. So with this approach, meaning that you have one system with nanoparticle that exactly have both function. So for example, with you have a receptor that actually you can label your nanoparticle, for example, with radionuclide. At the same time, you have drugs you encapsulate inside of it, and also if you use certain nanoparticle, for example, iron oxide, it have the magnetic property. You can use a thermal therapy to actually helping into killing the virus. So you have the drugs, or maybe you deliver the sRNA, knock down. So sRNA only knock down the RNA, and then you have the virus. I mean the nanoparticle that can be used for heat therapy. So for example, you give radiation or magnetic signal to the nanoparticle, you will produce heat and destroy the protein or destroy the structure of the virus. So it means that you have a multiple system, a multiple function in one system. So you have therapy system and you have a diagnosis system. So use the diagnosis to localize. Okay, now I know the virus is localized in the lung, or perhaps you might detect in the other organs, for example, in kidney, for example. And then okay, now you know the sRNA be delivered during the knockdown, so it destroyed the RNA of the virus. But no, you know the virus still exists, but without the viral genome. So you already localize, so in the lung or in the kidney. Then you do the, for example, here they give ultrasound radiation. So of course duration, they produce radical. So instead of you give radiation to the whole body, you already localize where are the virus. You only give radiation to that particular location. So you give radiation near to the lung, and you give radiation to the kidney. So you have a specific, like a precise treatment to the patient. So it helps for the doctors to actually localize at the same time treatment, and it's not just one type of treatment, it can become a double or triple type of treatment. So you can select drug, you can select sRNA, you can do the external stimuli into therapeutical, and so on. So the theranostics, the study of theranostic is not old, but it's not that much new. But still, a lot of people still discovering of this optimizing of theranostic nanoparticle. Mainly people are using theranostic for cancer treatment or cancer diagnosis, but now they say, why don't we use the same concept of theranostic nanoparticle, but we treat the COVID-19 patient? Because people already know the S protein is to the bounding, so you can bound with that, and then we know you bound. Then why don't we deliver sRNA to knock down the RNA of the virus? At the same time, we use external stimulation, for example, ultrasound or radiation, to actually kill the virus, because you already localize them. So these are the ideal of what that's why I said nanomedicine is a magical item, because like you can modify it, you can't. It's very universal. It depends on what your target and what material that you want to use, what you want to encapsulate of the drugs, what you want to deliver, and what methodology that you want to detect the virus, and so on. So these are some of the studies being done by scientists current at the moment, because we don't have much paper that already have the result. Okay, we managed to cure COVID-19, because as I said, case of COVID-19 is still new. It's just like about 6 months happened throughout the world, and then because of the lockdown of certain countries, certain scientists or researchers do not have any access to the laboratory because they prioritize for the frontline to the work. But now, after the 6 months happened, people are now accessing back to the laboratory. So I think with this kind of a new approach of treatment of the COVID-19 or the SARS-CoV-2 virus, we will see a new finding that will help not just in terms of the academic or research world, but actually help a lot of people to actually have a better life, and that we can have, I know people are facing a new normal right now, that we can have a better life afterwards. And then if people got infected by COVID-19 in the future, it will not become kind of like a heavy disease. Perhaps with all this finding, we will see COVID-19, we might treat them as a normal as normal influenza rather than a very heavily or high risk influenza. So that's some kind a small sharing from me.